Hello. In the last lecture, we are discussing about the modeling of a three-phase symmetrical synchronous machine. We will start from that. We have already seen the expression of inductances for the stator. When we have a silent pole synchronous machine, the air gap is non-uniform. So we have variation of inductance in the D and Q axis, and we have also seen the inductance between phase A and phase B of the stator, the self inductance of a particular phase, and these are actually function of the rotor position, that is theta r. Now we will briefly review the inductance expression for the stator and the rotor, the mutual inductance between the stator and the rotor, and we will start from that. Now if you see, this is actually a synchronous machine, a three-phase synchronous machine, where we have phase A, phase B and phase C, and the rotor is silent pole rotor, and this is our D axis and this is the Q axis, and we are now trying to evaluate the mutual inductance between the rotor and the stator. The rotor has got three windings. Two windings are in the D axis. We can see this is the field winding. So this is the field winding in the D axis, and this is the damper in the D axis. And then we have one winding in the Q axis rotor, that is the damper winding in the Q axis. So right now we will try to evaluate the inductance between the D axis field winding and the stator windings, that is phase A, phase B, phase C of the stator. Now if we take the inductance of the field winding with phase A, that is LAF, that's given as Lg0 plus Lg2 into IF into NF into cos of theta r by NS by IF, because inductance by definition is flux linkage per ampere. So the flux linkage is Lg0 plus Lg2 IF NF by NS into cos theta r by IF. Since Lg0 plus Lg2, this expression we have already seen in the last lecture, are referred from the primary side, we have to multiply suitable number of turns, and the number of turns is NF by NS. And if we simplify this, this is Lg0 plus Lg2 into NF by NS into cos of theta r, that is LAF, the inductance between phase A of the stator and the field winding. Similarly, we can evaluate the inductance between phase B of the stator and the field winding. It's basically a matter of phase shift. So we can see that this LBF, that is this inductance, is given as Lg0 plus Lg2 into NF by NS into cos of theta r minus of 2 pi by 3, because phase B is shifted from phase A by 2 pi by 3, and that is why we can see that we have a factor of cos of theta r minus 2 pi by 3 coming into picture here. And similarly we can evaluate LCF, that is Lg0 plus Lg2 into NF by NS cos of theta r plus 2 pi by 3, because phase C is further 120 degree ahead of phase B, and hence we have cos theta r plus 2 pi by 3. This is basically the mutual inductance between the field winding and that of the phase A, phase B, phase C of the stator. Similarly, we can evaluate the mutual inductance between the D axis damper and the stator winding. That is, say for example, if you have LAKD, the expression will be something similar, because the field winding and the damper winding in the D axis are in the same axis. So far as the angle is concerned, we have similarly we will have cos theta r for A phase and damper in the D axis, cos theta r minus 120 for phase B and the damper in the D axis, and so on. But what is different here is that the damper winding number of turns will be different from that of the field winding number of turns. In fact, in case of a synchronous machine, there is no physical damper winding. They are basically damper bars. So we have to effectively calculate the effective number of turns of the damper winding, and those number of turns will be taken into account for calculation of this mutual inductance. So LAKD is given as Lg0 plus Lg2 into NKD by NS into cos theta r. Similarly, LBKD, the mutual inductance between phase B and the damper winding in the D axis is Lg0 plus Lg2 into NKD by NS cos theta r minus 2 pi by 3. LCKD is equal to Lg0 plus Lg2 into NKD by NS into cos theta r plus 2 pi by 3. And similarly, we can also evaluate the inductance of the Q axis damper winding with phase A, phase B and phase C. There will be a negative sign because of the appropriate phase angle. So that will be cos theta r plus 2 pi by 3, and cos theta r plus 2 pi by 3 is minus of sin theta r. So we have Lg0 minus Lg2 because the Q axis permeance is something different, and that corresponds to an inductance of Lg0 minus of Lg2 into NKQ by NS sin of theta r. LBKQ is equal to minus of Lg0 minus Lg2 NKQ by NS into sin of theta r minus 2 pi by 3. Similarly, LCKQ equal to minus of Lg0 minus Lg2 into NKQ by NS into sin of theta r plus 2 pi by 3. And these are actually the various inductances between the stator and the rotor, but they are actual inductances. Now, we should remember that when we are talking about the parameters of a machine, it's always convenient to refer all variables from the primary side. It's basically a practice we have seen in case of a transformer, in case of an induction machine, and we can also apply the same principle for synchronous machine, that all parameters should be referred from the primary side. Now, when we refer from the primary side, we have to multiply appropriate number of turns. So that has to be taken into account when we refer all parameters from the primary side. And furthermore, when we are talking about a DQ system, we are transforming ABC into DQ. And in case of a synchronous machine, the stator is a 3-phase stator, and we have chosen a rotor reference frame. It means the reference frame is housed on the rotor. So if the reference frame is housed on the rotor, just like this, we can have a reference frame with D axis here and Q axis here, and it is attached to the rotor, rotating with the rotor speed that's equal to omega r. We have to transform all variables of the stator, physical stator, that is phase A, phase B and phase C of the stator, to D and Q axis. Of course, these axes are hypothetical. I mean, the windings corresponding to D and Q axis are hypothetical, but we have to transform the physical ABC variables, voltages and currents, to the D and Q axis current housed on the rotor. Because our reference frame is a rotor reference frame, we will have the following expression. So this is what we have here, that the flux linkage in this case is psi ABCS, and if you have the flux linkage in the stator, that is contributed by the stator self flux LSS into IABCS plus the contribution from the rotor side. So this is LSR. LSR we have already evaluated in terms of the various inductances. So if we put those inductances, that will be LSR. And then we have the rotor currents. They are the field winding current, the D axis damper and the Q axis damper. And we can pre-multiply this equation by CS, because we want to transform this into DQ variable, and to transform into DQ variable we have to have the transformation matrix, and the transformation matrix in this case is CS, and CS involves theta r is the rotor position. So if we pre-multiply by CS in this case, we have got CS into psi s. Psi s is same as psi ABCS, that's equal to CS. LSS is the inductance of the stator, CS inverse into CS. So this we are actually having the CS inverse into CS, because this will the same I matrix. There is no change of the value of the equation here. Into IS. IS is the stator currents, which are IAS, IBS, ICS. This is a vector, plus CS and I into L of SR. Now we can convert this SR into SR prime by suitably multiplying the number of turns into IF KD KQ prime. So when we multiply by suitable number of turns, we can convert the rotor currents into the referred currents from the primary side. This is what we have. Now if we see, this will be giving us psi dq os. This will be the d axis, q axis and the zero sequence component flux of the stator, and this will be L dq os, the inductance of the stator in the dqo frame, and then we have Cs into Is, we have I dqos, this will be IDS, IQS and IOS, plus we can have this as L F KD KQ prime into I F KD KQ prime. So this is what we have here, and we should be interested to know what are these matrices. These matrices are very special matrices. Unlike the previous matrices, that is LSS, which is a function of theta r, this LDQOS and LFKDKQ, they are independent of theta. They are basically constant matrices. We will see the expression of these matrices. So we can see here first LDQOS, and how did we obtain this? We obtain this by pre-multiplying with CS and post-multiplying with CS inverse. Now this matrix will have this expression. This is LAL plus 3 by 2 LG naught plus LG2. Here we have zeros and zeros, and then the next row is 0 LAL plus 3 by 2 LG naught minus LG2, 0, 0, 0 and AL. This matrix is the stator inductance matrix of the DQ reference frame of a synchronous machine. Now if you see this, the stator inductance LDS in the D axis is given as LAL, is the leakage inductance of the stator, plus 3 by 2 times LG naught plus LG2. Now we see that this is independent of theta r. So this is interesting to note that this inductance is not a position dependent. This is independent of theta r. It's a constant inductance. Okay, and we can call this in this particular fashion LAL plus LMD. LMD is equal to 3 by 2 times of LG naught plus LG2. Similarly, the second inductance LQS is equal to LAL plus 3 by 2 times of LG naught minus of LG2, and that's equal to LAL plus LMQ. This is LMQ. This is basically the Q axis magnetizing inductance, which is again constant, which is not a function of theta r. So that is the beauty of the transformation. When you transform the variable to the rotor side or the rotor reference frame, we see that by the rotor reference frame, when we transform ABC variable into DQ variables, the inductances are constant inductances. And LAL here is a zero sequence inductance. So we can say that LOS is equal to LAL. The zero sequence inductance is just the leakage inductance, which is a small quantity. It is not a large value, it is a small value, and it is again constant. Now if you see the rotor, we can see this rotor inductances LF KD KQ prime. Now this inductance would be of this form. So we have in this case 3 by 2 into LG naught plus LG2, and then we have here also 3 by 2 Lg0 plus Lg2, and then we have 0, and then we have in the d axis also we can find out that this for the q axis 3 by 2 Lg0 minus Lg2, 0, 0 and 0. So this inductance is the inductance in the dq reference frame between the stator and the rotor. Now by this special transformation, the currents of the rotors also get changed. The voltage of the rotor also gets changed, because we are referring everything from the primary side in the dq reference frame. Now the rotor currents will be If prime is equal to 2 by 3 times of Nf by Ns into the actual If. You can see that we have a factor of 2 by 3 coming, because the rotor is a 2-phase rotor and the stator is a 3-phase stator, and when we are transforming into the stator side, there is a 2 by 3 factor coming to picture here. Similarly, Ikd prime referred from the primary side is equal to 2 by 3 of Nkd by Ns into Ikd. Ikd is the actual damper winding current in the d axis. When we refer that from the primary side, it will be Ikd prime, that's equal to 2 by 3 times of Nkd by Ns. Similarly, we have Ikq, that's equal to 2 by 3 times of Nkq by Ns into Ikq. These are the currents which are referred from the primary side. And similarly, we can also have the expression for the resistance. The voltage, of course, Vf referred from the primary side is given as actual Vf into Ns by Nf. And if we see the various parameters, the referred value of resistance is given as Ns by Nf whole square into the actual resistance, and this will be multiplied by a factor of 3 by 2. Similarly, Rkd prime is equal to 3 by 2 times of Ns by Nkd whole square, actual damper winding resistance in the d axis, and Rkq prime is equal to 3 by 2 times of Ns by Nkq whole square into Rkq, and Rkq is the damper resistance in the q axis. The leakages are also transformed in the same way. Say for example, if I say that LLF, the leakage of the field winding inductance, that's equal to 3 by 2 times of Ns by Nf whole square into the actual leakage inductance of the field winding. So these are actually the parameters as reflected from the primary side in the dq reference frame. Now what we actually do in the equivalent circuit, we don't have access to the actual parameters of the machine. What we actually use, we use the referred parameters since from the primary side, and hence we use Rf prime, Rkd prime, Rkq prime, LLF prime, LLkd prime, and LLkq prime. So we can write down the flux linkage expression. Psi ds is the flux linkage in the d axis, that's equal to LDS IDS plus LMD into IDS plus IF prime plus IKD prime. Similarly, we have psi QS equal to LLS into IQS plus LMQ into IQS plus IKQ prime. This is the leakage inductance. So we have LAL or LLS. This is the same thing. This is the leakage inductance of the stator. the field flux are referred from the primary side, that's equal to LF prime into IF prime plus LMD into IDS plus IF prime plus IKD prime. The damper winding flux linkage seen from the primary side, that's equal to LKD prime IKD prime plus LMD into IDS plus IF prime plus IKD prime. Damper winding flux in the Q axis as referred from the primary side, that's equal to LQ prime IKQ prime plus LMQ into IQS plus IKQ prime. So these are the various flux linkages with the windings of a synchronous machine. Now these flux linkages will be used to determine the voltage equation. Now if you remember, we have chosen a rotor reference frame. The rotor reference frame is revolving with the rotor at a speed of omega r. And hence, in the stator equation, we will have the speed induced EMF appearing, and the stator equation, in addition to the statically induced EMF, will also have speed induced EMF. So we will now write down the stator equations in the DQ reference frame. So if we write down here VDS, that's equal to RS IDS plus P psi ds minus of omega r psi qs. The expression of VDS and VQS are given. These are the stator equations. We can have VQS equal to RS IQS plus P psi qs plus omega r psi ds, and the expression of psi ds is already given here. And the zero sequence equation, we can write RS IOS plus P psi OS. The zero sequence is neither coupled to D axis nor to Q axis, and hence the zero sequence will not have any rotational induced EMF. The plane of the zero sequence winding is orthogonal to both D and Q axis in a different plane. It can be considered in the Z axis. If the D axis is X axis and the Q axis is Y axis, the zero sequence component can be the Z axis, and hence the zero sequence component does not have any coupling with D and Q axis, and it doesn't also take part in torque production, and hence we need not solve the zero sequence current expression. Similarly, for the rotor, we can say VA prime, that's equal to RF prime IF prime plus P psi F prime. The rotor will not have any rotational induced EMF because the rotor and the reference frame are stationary to each other. There is no relative velocity between the rotor and the rotating reference frame, and hence the rotor equation will not have any rotational induced EMF. We can similarly have VKQ prime equal to RKQ prime IKD prime plus P psi KD prime, and VKQ prime is equal to RKQ prime IKQ prime plus P psi KQ prime. And these equations can be written in a matrix form. If you write this in a matrix form, the equation will appear as follows: VDS, VQS, VF, VKD, VKQ, all referred from the primary side. And here we have the various currents. And the currents are IDS, IQS, IF, IKD, and IKQ. Now, this is a 5 by 5 matrix, and we can fill up the various elements of this matrix, and the elements are as follows. We have the various rows in this case, the third row, the fourth row, and the fifth row. So, this is the first column, the second column, the third column, the fourth and fifth column. This is a 5 by 5 matrix. We can fill up this by inspection. Now, this is the stator resistance drop plus the self inductance drop, LDS, and LDS is equal to LLS plus LMD, and we will have the coupling with the D axis rotor. It is LMDP with the rotor, LMDP with the D axis damper, and then we have the rotationally induced EMF. This will be minus of omega r into LQS. This is minus of omega r into LMQ. Similarly, the second row would be LS plus RS plus LQSP. Now, we have the coupling with the Q axis. This is LMQP, and then we have the speed induced EMF or the rotationally induced EMF, omega r LDS, omega r LMD, omega r LMD. So, these two rows are for the stator, and the three remaining rows are for the rotor, and the rotor equations and the corresponding elements can also be written similarly. This is the field resistance Rf prime plus Lf prime P. Now, this LQS is the Q axis inductance of the stator, that is LLS plus LMQ, and LF is the field winding inductance, that is equal to LLF prime plus LMD. Similarly, we can have LKQ KD prime, that is the D axis damper inductance, that is equal to LKD plus LMD, and LKQ prime is the Q axis damper inductance, that is equal to LKQ plus LMQ. So, we were writing the third row. In the third row, we have Rf prime plus Lf prime P, and this will be having the coupling with the D axis damper. We have LMDP and the D axis stator, LMDP, and there is no rotationally induced EMF in the rotor. So, we have zeros here. Similarly, in the D axis damper, we have RKD prime plus LKD prime P. LKD is the D axis damper inductance, and similarly, we can have the coupling of this with the field winding and also with the stator D axis, and there is no rotationally induced EMF. So, we can put this equal to 0. The fifth row would be for the Q axis damper, RKQ prime plus LKQ prime P. P is the derivative operator, as we know, and this will have the coupling with the stator winding, that is LMQP, and there is no rotational induced EMF. So, we can put this equal to 0. So, this is a 5 by 5 matrix, and this 5 equation will describe the electrical behavior of a synchronous machine. So, if we can simulate this 5 simultaneous differential equation, we can solve for IDS, IQS, IF, IKD, and IKQ. So, we can solve the expression for the currents of the synchronous machine, and with this we can find out the expression for the torque also, because In this case, we have to identify a G matrix. So we know that the expression for the torque TE is equal to 3 by 2 P by 2 I transpose matrix G into I. This is actually as per the primitive machine equation. The equations of the Cron primitive machines give us the expression for the torque. And since we have a 3-phase machine and we have taken a transformation with per phase power invariance, when we calculate the total torque, we have to multiply 3 by 2 to find out the torque of the actual 3-phase machine. So we have 3 by 2 times the P by 2 is the pole pair, I transpose, G matrix is the matrix associated with the speed term into I. I is a vector and I consists of the stator currents and the rotor currents. So let us see what is this G matrix. This G matrix we can find out from the previous expression. From this we can find out the G matrix, and the G matrix will have these elements, the speed terms. All the speed terms will give us the G matrix. So if we see here, this matrix G can be 0 minus LQS 0 0 minus LMQ, and then we have LDS 0, LMD 0. Remaining 3 rows are for the rotor, and the rotor does not have any rotational induced EMF, and hence the speed term are absent in the rotor. So we have, this is a G matrix. Now if we pre-multiply with I transpose and post-multiply with I, we get the torque. T is equal to 3 by 2 into P by 2 into I transpose is IDS, IQS, IF, IKD, IKQ, and then I have this G matrix into I, IDS, IQS, IF, IKD, and IKQ. If I simplify this, I will get the expression for the torque. Let's see. So we can simplify this, and we will get the expression for the torque. So this we can pre-multiply. So we have got 3 by 2 into P by 2. If we pre-multiply this, so we have LDS IQS minus LQS IDS, and then the third row will give us LMD IQS, and the fourth row is also LMD IQS, and the fifth one will give us minus LMQ IDS, and that is multiplied by this equation I. So if we simplify this, we get 3 by 2 into P by 2. So we have LDS IQS IDS minus LQS IDS IQS plus LMD IQS IF prime plus LMD IQS IKD prime minus LMQ IDS IKQ prime. So this is the expression for the torque, and this torque we can further simplify, and we can separate this into 3 different terms. So this part we can write in the following fashion: 3 by 2 into P by 2. So the first part is LDS minus of LQS into IDS into IQS. Now, this is called term 1. So, we can call this to be term 1. And this torque is called the reluctance torque, because this torque is a function of LDS minus LQS. So, if LDS minus LQS is equal to 0, this torque vanishes. And the second term we can take as LMD into LQS IF prime. LMD into IQS into IF prime. Now, this is the term 2, and this is called field winding torque, because this is basically by virtue of the field winding the torque is produced. If IF prime equal to 0, if there is no field winding current, this torque also vanishes. So, this is called the field winding torque. And what about the third torque? We can see the third thing, LMD IKQ IKD, LMD IKQ IKD minus LMQ IDS IKQ minus LMQ IDS IKQ. So, this is the third torque here, and this is called the term 3, and this is called the damper winding torque. This is called the field torque, and this is called the reluctance torque. So, the synchronous machine will have 3 different torque: the reluctance torque, the field torque, and the damper winding torque. So, we will now draw the equivalent circuit of the synchronous machine in the DQ reference frame. We have seen that the actual machine can be transformed into a hypothetical machine in the DQ frame attached with the rotor, and this is for our convenience of simulation. So, we can have the equivalent circuit of the synchronous machine in rotor reference frame, and this will be used for the simulation of synchronous machine. So, we can do that. Equivalent circuit of synchronous machine in Park reference frame. So, we can first draw the D axis equivalent circuit, and we will expect that in the stator we will have rotationally induced EMF, in the rotor we should not have any rotationally induced EMF. So, we have the resistance here, and then we have the rotationally induced EMF, the stator leakage, the magnetizing inductance, and then we have the damper winding, and the damper winding is usually short circuited. We have the field winding, the field leakage inductance, the resistance, and we have the field applied voltage. So, this is our VDS, the applied voltage in the D axis stator is the stator resistance, and this is IDS, the stator current. And this is the rotationally induced EMF, this is the leakage inductance of the stator, this is the magnetizing inductance in the stator D axis, the damper leakage inductance LKD prime referred from the primary side, damper resistance referred from the primary side, the field leakage inductance referred from the primary side, the field resistance referred from the primary side, the field voltage referred from the primary side. Now, we will now write down the expression for the rotationally induced EMF in the stator. So, this will be a function of omega r, and in the D axis the rotationally induced EMF will be, because of the q axis flux, omega r into psi QS, and this will be helping the applied voltage. So this will be minus here and plus here. In a similar fashion, we can draw the Q axis equivalent circuit. Resistance, the back EMF in the Q axis, the leakage inductance, the magnetizing inductance in the Q axis, and then we will have the rotor, and the rotor is the damper winding only. So this is our Q axis equivalent circuit. VQS is the stator Q axis voltage, the resistance is RS, and this is IQS is the Q axis current. We have rotational induced EMF. This is the stator leakage inductance, the magnetizing inductance in the Q axis, the damper leakage inductance LLKQ and RKQ, and this rotational induced EMF will be omega R into psi ds. This will be in fact opposing the applied voltage, and hence the sign will be plus here this side and minus in the right hand side. And the various fluxes here we have, this is basically the stator flux linkage in the d axis psi ds, which includes the mutual flux and the stator d axis leakage flux. Similarly, this one is psi qs, the q axis stator flux linkage, which consists of the mutual flux and the leakage flux. This is the damper winding flux linkage psi kd prime as seen from the primary side, which consists of the damper leakage flux. This is your damper current IKD prime, and this is the field flux linkage psi f. This is IA prime, the field current. So we have shown the various flux linkages in the stator as well as in the rotor, in the d axis. Similarly, in the q axis, this flux linkage is psi kq, which consists of the q axis damper leakage flux. This is the damper current IKQ prime, the leakage flux plus the magnetizing flux in the q axis. So psi kq prime, as referred from the primary side, is the flux linkage in the q axis damper. So we have the complete equivalent circuit in front of us. So we can use this equivalent circuit to solve the various current expression. And of course, we know that we have two systems. Here we have an electrical system, also we have a mechanical system. In the mechanical system, we have to solve for electromechanical equation, that is the torque PE is given as J d omega r by dt by P by 2 plus B omega r by P by 2 plus TL. PE we already know, this is the torque of a synchronous machine, and we will be equating that to the inertial torque, the viscous friction torque and the load torque. Now if we solve this equation, we will get the expression for the rotor speed, that is omega r, and we can integrate this omega r to get the expression for the theta r. So this is what we have here. We can have some initial constant, the initial position, so the integration of omega r dt will give us theta r, and the theta r can be used to transform the actual voltages VA, VB, VC into VD and VQ. We can simulate the machine in the DQ equations in the Park reference frame, evaluate IDS, IQS, IF prime, IKD prime and IKQ prime, and this has to be an iterative process, and we have to take the help of a numerical integration technique to solve the current expression for a synchronous machine. Now you must have noted that the synchronous machine is more complex than an induction machine. An induction machine had 4 currents: IDS, IQS, IDR, and IQR. On the other hand, a synchronous machine has 5 currents: IDS, IQS, IF, IKD, and IKQ. So we have, in addition to the field winding current, we also have the damper winding currents, and that's why it is more complex. And again, we have to also apply a voltage from the field side, and hence it is more complex than that of an induction machine, and the simulation will take more time than an induction machine. So these are the equations. So we can use this equation to simulate a synchronous machine. So with this, we come to an end of the modeling and of a synchronous machine, and with this also we finished the modeling of DC machine, induction machine, and synchronous machine. So the next part of this particular course will be the control of electric machines. The title of the course is Advanced Electric Drives. We have seen how to model various electric machines. We have the models available with us, and we can use this model to think of innovative control technique to improve the torque and speed response of AC machines. So the control will primarily focus on AC machine. The first machine that we are going to control is an induction machine. So we will talk about a control that is called vector control of induction machine. This vector control is not a new way of controlling induction machine. In fact, the very concept, the principle, was given sometimes in 1969 by a scientist called Félix Blasquet. The Blasquet gave an idea to a control of AC machine called field oriented control. And this was also known as vector control because we are controlling the amplitude, the frequency, and the phase angle of the currents in the stator. So this is known in various names. One is a vector control. This is also called field oriented control. It is also called transvector control. And sometimes people also call this as decoupled control or decoupling control. Usually, an induction machine is having 3 windings: phase A, phase B, and phase C. So if you see an induction machine, this is the rotor, and we have 3 different windings: phase A, phase B, and phase C. And the rotor could be a squirrel cage rotor. We have the rotor conductors, and this machine is a highly nonlinear machine. And this can be only controlled by some advanced technique, and we can control this machine like a separately excited, fully compensated DC machine using vector control. So what we are trying to do here, the objective is to control an induction machine just like a separately excited DC machine. So this control has to be done just like a separately excited DC machine. We have a DC machine here, an armature, and a field winding. Just have a comparison in this case. We have the armature current IA, and we have the field current IF, and these 2 currents are orthogonal to each other. This is the axis, and we can call this to be D axis. This is Q axis, and this angle is 90 degree. And we know that the torque is given by a simple expression like K into